maximum number of people that can be paired up. Okay? So now, can you think of a way to solve this problem? Yeah, somebody should, you can lift your hand and yeah, go ahead.
Create a source and a sink which have infinite capacity to do that. That goes once the source goes to all the boys and the sink, all the girls go into the sink. And each edge between the boys and the girls each have capacity of 1.
Right.
And then if you maximize that flow, you find the maximum height.
Okay, so what should be the capacity on the edges going from S to each of the boys?
1.
Or can you said initially it said it could be anything.
Yeah.
So should it be 1 or could it be anything?
No, it should be 1.
And someone else, can you tell me why it should be 1 and not say 2? What would happen if, let's say, I allow the source to send 2 units to Al? Right, then he can marry 2 girls, right? So that's the problem, right? We want matching. So which means that we want to make sure that if Al is part of the matching, that means Al should be sending something to 1 girl and only 1 girl, right? So as a result, the way you solve this using this max flow algorithm is that you create a source, and from the source you're going to add an edge to each boy or each element of the first set, okay? And these edges are going to have a capacity of 1, and all the edges that are already shown, they all have a capacity of 1, and then on the receiving side, the sink is going to have an edge to each of the elements of the second set, and once again all those edges are going to have the capacity of 1. Okay, so so you have an S, and every edge has capacity 1, so I won't write that and clutter up the picture. And same way here we have it's indiscriminate. Okay, so can you tell me how would you figure out whether there is a perfect matching or not? Okay, so we have posted as a mass flow problem, and of course we are trying to maximize the flow from S to T, but how would we know whether we have a perfect matching or not? Well, can you try to be more precise? So one of the things that I want you to do is to try to be more precise. What is the N? I don't know what N is.
Number of boys.
So if the flow that I'm able to get pumped through is equal to the number of boys or the size of one of the sets, then I know, okay, that is a perfect match. Okay, and of course, so, or in other words, if the amount of flow I can get through is equal to the degree of S and degree of T. Okay, so both conditions are required, right? So if the degree of S equals degree of T equals the amount of flow that I can push through, then I know that I have a perfect match. Okay? If I don't have a perfect match, then I have a maximal match. Okay? So you can see that because of the nature of the paths, right? You can see that no boy can be matched with more than one girl, right? So that's clear. And it's going to, because it's going to compute the maximum flow, right? And this is obviously a cut, right? This is obviously a cut in the graph. So the maximum flow is going to maximize what can flow out through these edges, right? What can possibly be sent through these edges. And therefore, the max flow is going to maximize, because all edges have the same capacity, maximizing the flow across this cut set is equivalent to saying maximize the number of edges that are carrying any flow. Okay? And so that tells you that, in fact, it's going to produce a maximal match. Okay? So, of course, one might ask, okay, so far we didn't say anything about whether the algorithm computes integral solutions or not. Okay, but obviously you know from the nature of the problem that if the edge weights are integral, because we are always taking the min, right, of the edge capacity on a path, so obviously it's going to compute only integral solutions if all the edge weights are integral. Okay. The reason why I even try to point out is that in general, a number of problems are solvable when you express them over the domain of real numbers. But if you restrict the solutions to be in the domain of integers, the problems often become very hard. Okay? So, can you tell me an example of a problem that we have encountered where it was efficiently solvable in the real domain but not in the integer domain? The knapsack problem, right? So we said fractional knapsack, no problem. We have a very efficient greedy algorithm. Integer knapsack, sorry, it's NP complete, right? It's an NP hard problem. Okay, so same way one might, if you think about linear programming has an efficient solution. We know that simplex itself is not efficient. It's a worst case exponential time algorithm, but there definitely exist polynomial time algorithms. So linear programming on the real domain is solvable in polynomial time. But if you want to do integer programming, where you again have linear relationships, but all the variables are constrained to be integers, then that is not solvable efficiently. It's another NP hard problem. Okay, and so one might naturally have this question. Okay, well, when I think of this max flow problem, it's natural to think of it in the domain of real numbers. Now, if I go to the domain of integers, it doesn't make it inefficient, but as it turns out that it doesn't matter for this problem whether it's integers or reals. Okay, so let's before we stop, let's think about. Let me ask you about a couple of other problems before we stop. Okay, suppose you have a problem where you have multiple sources and multiple sinks. Okay, so how would you solve that problem? The algorithm we have considered so far allows for a single source and single sink, right? Because we are always looking for S to T paths. So that means there is a single source and single sink. So how would we solve the problem if you have multiple, let's just say multiple sources? Yeah, go ahead. Okay, so we can do a simple construction where we add a new source, which is sort of what we did for biquadrate graph problem, right? So we did that And bipartite graph problem could actually have been thought of as multiple sources, multiple sinks problem, right? And what we said was, okay, because the toolbox we have only knows about one source and one sink, we transform the problem to solve it using that particular algorithm. And the same way we can do again, we can add a new source. Okay, now what should be the edge capacities from that source? So you want to, basically the intuition is that